Hi, Frank. Good to see you.
I was just about to send you a message to say it's a long time since I saw you. Nice to see you. It saves traveling, but it is not so interesting because you don't get to enjoy the venue.
Yeah, and we cannot take you out and have a lunch and that sort of thing. So,
well, hopefully one day.
Yeah, that's true.
On the other hand, I'm finding it's interesting the range of places that you can now follow talks from, that you can get talks from the States and things. And I see Chris Cortes-Altis has just arrived.
Yeah.
Hi, Chris. You have to unmute Chris in order to answer.
Chris, you're muted.
Chris, you're muted.
You're now in good shape.
Hopefully after.
Yes. Yeah, after England. Yeah. Sure.
Yeah.
Okay. Very good.
A huge amount of overexcitement. So they've won one match against Germany in 50 years. When they can do it on a regular basis, it might be more worth it getting excited about.
Yeah. And there was this one guy who played for Germany, but who was brought up in Britain.
Yeah.
Which was bad for the Brexit people, I suppose.
I was just thinking actually last night that I don't think it was the last time that I was in Amsterdam, but I remember very clearly being over in 1997, the night of the election when Tony Blair got elected. And I was exhausted the following morning because I had been listening to the election results on long-wave British radio through the night as the Labour Party gradually replaced that horrendous group of people that had been in power.
Yes.
So I announced the fact the following morning at the start of my talk, and everybody immediately burst into applause. I thought they were happier days.
Yes, right. I was in Oxford when Tony Blair won.
Ah,
I remember. Yeah. Anyway,
I don't recall when it was. Was that you were in Amsterdam for a conference?
I was giving a talk, whether it was at Nikhef or the university, I can't recall. All I can remember was being in a hotel room the previous night and just staying up late to listen to the radio, and then just being awake all night long listening to the results, then falling asleep in the middle of my talk. So
we have gradually arriving some more audience. Happy to see you, and we'll wait a few minutes for some more people, and in the meanwhile chat along about the past or the present or the future. I don't know, football, particle physics, it's all the same, right?
You can tell me, this is a series of talks that you're having, during this year, during this summer, or?
No, we decided as Nikhef closed down for a lockdown in connection to COVID-19, we decided to have regular lunch talks every Wednesday, more or less, with guests from inside and outside the Institute, to keep people connected and have nice, stimulating stories from all kinds of people. We have a small mini program inside our lunch talk program, which is neighbors of the Institute talking about their institute. You normally don't get to meet them except for over a lunch and saying hello, but explaining what they do, etc. is actually, it's quite fascinating and really surprising every now and then.
Well,
so we're making friends as well.
Good. Well, I mean, before we start or get lost, if there are other talks about the 50th anniversary of the Standard Model, can you send me an email and a link so that I could actually listen in as an external, or is that allowed?
Of course, yes, but I don't think we have any other talks scheduled right now, except from perhaps a symposium later on this year. Right. But I'm sure you'll get an invitation for that.
Okay. Thanks. Okay, I'll mute myself now until you tell me.
Frank, I use often a slide with a 50-year standard model, and the nice thing is you can use that for many years, I would say, because
Yes.
it was a little bit fake, but you might tell about it.
Yeah, I agree with you. It's a bit like fusion. You know, you can always say it's going to be 50 years from now.
Yeah. And for fusion, that's been true for the past 50 years, right?
Yes.
Yeah.
Hello, Frank.
I hear a voice. Who's
Karel.
Karel Gamers.
That's right. Nice to see you.
That's mutual.
Gosh,
I'm
very impressed. I'm impressed with your study and the books and things that you have there. Very good. Right. Okay.
Okay, let's see. It's a bit past.
That thing there is a model of the proton with 3 quarks that you can see just above my finger. Right. I'll mute myself and wait for you to call me.
Yes. Okay. I see Gilliam as well. Hi. Good to see you. So we have some external visitors as well. We have also a streaming going on at the Nikhef TV website. You might want to follow that, but the people from inside are more than welcome to join us at the Zoom. We have every, let's say, Wednesday, a series of lunch talks. Welcome to many people already, and hopefully some more will arrive as we are waiting to start I think, a nice presentation by Frank Close. Frank Close is a theoretical physicist. He's an emeritus professor at Oxford from Exeter College. And I discovered he actually was more or less a predecessor of people like me, as he was the director of communications for a short while at CERN as well, somewhere in the around 2000, I guess. And of course, Frank is really well known as a physicist, not only, but also as a communicator. He's written an excellent series of books on particle physics and theoretical physics. For a broader audience, I would say they're concise, they're very nice to read, and I think it's really worthwhile to put some time in that as a reader. I especially enjoyed a book he wrote in 2011, which is called The Infinity Puzzle, which relates more or less the history of finding the standard model. And Frank has been around for long enough to have seen some of it himself, and he talked to many people for the book. I can show you the book. This is my version. It's really good. And if you like to know more about the history than Frank even can tell in 1 hour, read it. That's an advice. Actually, the book came out in 2011, which is quite interesting because that was before the Higgs particle was discovered formally. So he wrote a new epilogue, and republished the book in 2013. But nevertheless, this is all quite some time ago, and we're here for some history of the standard model. Theoretical physics doesn't fall from trees, it's being done by people. And that's, I think, the main message that Frank will explain in the next hour or so. I would suggest that we listen to his talk first and have questions afterwards. On Zoom, that's the best way to proceed. So without further ado, I'd like to give the floor to Frank Close. If you share your screen, we can go ahead.
Right. Right, you. Okay, everybody there?
Yes, that's nice.
Okay, thanks. I'll just try to get rid of all of you so I can see the picture myself. Okay, thanks very much. Well, yes, you mentioned the Infinity Puzzle. I thought I'll get my commercials in at the very start. I'm currently completing a book about Peter Higgs and the Mystery of Mass, to be published next year on the 10th anniversary of the discovery. That's Peter Higgs in the photograph. I will not tell you who the other person is. If you don't know that, you shouldn't be here. Other than to say that's a sort of Schrodinger's cat type picture, because I took it at Erice about 10 days before the discovery was announced. So we were in that strange situation where the 5 sigma data were all still inside the box, but nobody had yet opened the box to see what the answer was. I thought I would start. Right, so that's okay. I call it the dawning of gauge theory, really. Going right back, the beginning of quantum electrodynamics. QED was created by Dirac primarily back in 1930 or so, and after its initial success, rapidly ran into problems the moment you try to calculate beyond the lowest order and started producing total nonsense like infinity for the probability of various things. And it wasn't until 1947 that a viable theory was finally formulated with the discovery of what we now call renormalization. And the people primarily associated with that, shown there on the cover of that magazine, Feynman, Tominaga, and Schwinger shared the Nobel Prize for the foundations of viable QED. Dyson, the fourth man who did not share the Nobel Prize, is the person who probably primarily proved that it was viable, using in particular the Ward identities. And I show you at the top there, John Ward, a person who probably many of you have never seen, other than know of him via the Ward identities. And as we will see, he's another person who ended up being the fourth man who missed out on Nobel Prizes. But the key, at least for the start of the talk, the key to the whole viability of QED, which Schwinger in particular was fascinated by, was the role of gauge invariance and the fact that gauge invariance linked with the photon, the carrier of the electromagnetic force, being massless. And at least my generation were taught that gauge invariance and massless photon were the same thing. We now know that's not true, but that's what we all believed, and indeed Schwinger and people believed for many years. The second development in this story is 1954, with the generalization of QED to what's called Yang-Mills theories. Instead of having your photon electron vertex being described by a number, like the number of coulombs of charge, to generalize that to a unitary matrix, so that you could, in particular, describe processes where charge is transferred from one particle to another. And these were originally developed by Yang and Mills, hence Yang-Mills theory. The problem with this immediately was that, of course, the analog of the photon is now carrying electric charge and is massless, and there are no such things, a fact that famously almost destroyed Yang's career. He was a very young man at that time. He gave a talk about this idea in front of Pauli. Pauli had also obviously been thinking about this and realized this problem with the massless charged gauge bosons, and demanded to know where they were. And Yang couldn't answer and almost had to stop the seminar on the spot until he was encouraged to carry on. But that was indeed the problem. Now, everybody knows of this as Yang-Mills theory. Well, not everybody. In the UK, we know of them as Yang-Mills-Shaw theories, because actually Shaw developed the idea before Yang and Mills. And Shaw is interesting in this story for various reasons. I was going to say there's many things in this talk that you will know already, but people never object to being told things they already know. But I hope there'll be some new features of them, historically at least, that you might not be aware of, in particular, the role of Shaw. Now, Shaw was a student of Abdus Salam, and Abdus Salam would come into his office all the time with crazy ideas, so much so that Shaw tried to avoid Salam as much as possible and spent his time in the library. And while he was there, one day, as this letter that he wrote to Schwinger much, much later in 1995 recalls, he found an old-fashioned preprint. Those were the days when your original ideas were printed out and photocopied many times and sent around the world. And he wrote to Schwinger, "You will note my own ideas were stimulated by a preprint of yours around 1953. My memory of this, what it is worth, blah, 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 blah." Shaw had met the idea of what we now call SU2. And he had the idea of taking what Schwinger was trying to do and putting it into what we call SU2 language. And as a result of that, developed the beginnings of what we now would call Yang-Mills theory. And he spoke to Salam about this, and he never published it. And the reason he never published it, well, here is a letter from Salam to Shaw, written years later, at the bottom of which he says, "I still remember asking you to publish this, and you were very shy at that moment because you thought Yang and Mills had already published it, although you had done the work independently." And indeed, that is the case, that Shaw had done the work first, but he didn't publish because he later learnt that Yang and Mills had done it, and he only published it in his thesis. Now, for most of us, that would be a terrible thing. For sure, he was very sanguine. He told me when I was writing Infinity Puzzle many years later, "I'm quite glad of not having my name added to Yang and Mills. I like a quiet life and would not have enjoyed being pestered by lots of queries from researchers expecting me to be up to date on the latest developments." So that's sure the first little bit of intriguing history in this saga. So now let's move on to 1956 and Schwinger. Schwinger had been worried, I was going to say perturbed, but that's probably the wrong word in the present circumstances, for several years about the link between gauge invariance and the massless photon. He was able to prove that connection in perturbation theory, but he wasn't able to make a general proof. And he was beginning to wonder if indeed it was generally true. Of course, today we know it wasn't, but pretend we're still back in 1956. Meanwhile, he was also fascinated with the idea of making a theory that would unify, in some sense, electromagnetism and the weak interactions by inventing analogues of the photon, which we will call W plus and W minus. And it was basically little more than numerology. The fact that the weak interactions at low energies, which is all he then knew, of course, are weak compared to electromagnetic, was naturally explained by him by allowing the W bosons to be very massive. So that was just a model that he had, a photon, two massive Ws, end of story. Then one day, 1961, he took on a new student, Shelley Glashow. And Glashow recalled years later, "Schwinger told me to think about unifying weak and electromagnetic interactions. So I did. For 2 years, I thought about it." And that was pretty well going to be the end of the story. But what Glashow did, we all know, eventually won him a Nobel Prize. But the things that got him there, I found sort of intriguing. And so let me just tell you what you may already know, but let me just touch on it anyway. So here we've got Schwinger in 1956, W plus, W minus, and photon. And Glashow is now thinking about the whole business of unifying. The key thing, it turns out, for Glashow was the fact that empirically, the charged weak interactions violate parity. It's intriguing to me, in parenthesis, if parity hadn't been violated, what would have happened? But parity was violated. And this told Glashow that the photon, which does not violate parity, couldn't be a simple partner of the W plus and W minus. Now, you or I probably at this moment would have stopped totally, saying, well, this idea clearly isn't going to work. But Glashow was young, had chutzpah, and he thought, okay, I will suppose that there is another particle that is the neutral partner of the W plus and W minus. And like New York, so good they named it twice, he called it Z for zero and gave it the zero charge as well. So he invented the idea of the massive Z solely because of the fact that parity was violated in the charged weak interactions, and hence he assumed there had to be some other neutral partner of the Ws, which was not the photon. And although he didn't realize it at that time, he had written down the beginnings of what becomes known as SU2 cross U1, with the W plus W minus the Z and also the photon. Of course, there is a little problem here, namely that QED with the photon is renormalizable because of gauge invariance and the massless photon. Whereas Glashow has now got massive Ws and Zs. And so the problem of gauge invariance and massive gauge carriers is a problem. And again, this again is something that probably would cause you or me just to stop. But Glashow, being a brave young man with nothing to lose, just announced, this is a problem we will ignore, which indeed, as things turned out, was the right thing to do. Okay, so let's put that story on one side and come back to it in a minute or two while I tell you what was developing in parallel with Ward and Salam, who are the other half of this tale. Warmly admired, richly deserved is the telegram that Ward apparently sent to Salam when Salam won the Nobel Prize, for which Ward was excluded. And so this story really is how Salam's name came in first and how Ward disappeared, and eventually how it was that Higgs became so prominent. So Ward, I should just say two things about Ward. Ward was indeed a real genius. I mean, the word is used casually, but Ward, with his identities and other things that he did, was indeed a remarkable person. Sakharov regarded him as one of the titans of QED. The second thing you need to know about Ward was that he's not the most reliable of witnesses. So I'm only able to tell you here what he claims the history was. Now, parity violation to Ward realized that parity violation would be natural if the weak interactions were described by both vector and axial currents in a V minus A, the standard thing that we all know and love today. So he realizes that parity violation suggests that there is a vector aspect inside the weak interactions, which is also shared by electromagnetism. And so he then suggested to Salam the idea that they should try to unify weak and electromagnetic interactions. This is 1957. And by 1961, they had produced their model, which didn't have any Z. It just had a W plus, a W minus, and the photon, no mixing angles. And in modern language, it was a U3 model. But that's where they were in 1961. And of course, unknown to them, Glashow across the Atlantic has written down SU2 cross U1 with a Z and a weak mixing angle. So that's where Salam and Ward were in 1961. Now, they didn't know of Glashow's work, apparently. They never read his paper, apparently. 3 years later, they had produced pretty much the same thing, an SU2 cross U1 model with a Z boson and a weak mixing angle. The point of this is just to say this is 3 years after Glashow has done his stuff. I thought I'd just show you this sort of handwritten manuscript of Salam and Ward, electromagnetic and weak interactions. Just to note, there's an abstract there on the left, and it begins one of the recurrent dreams, and there's lots of crossings out. It just shows you how much thinking goes in those days. You didn't have word processors. But compare with the actual paper, which is a physics letter without any abstract, this shows you that obviously their original idea was to produce a full paper, and it ended up being a letter. This is their 1964 paper with their SU2 cross U1 model, which in modern language is correct. Unfortunately, of course, Glashow had already got this 3 years earlier, but that's where we were at that stage. So now let's make a link again with the story that we just left, the problem that Schwinger was worrying about gauge invariance and massless photons, which he was only able to prove in perturbation theory, but not in general. And it seems that by the end of the 50s, around 1960 or so, he was beginning to doubt whether there is a general proof. In fact, he was beginning to suspect that there is no general proof. But he wasn't able to pin that down. Of course, we now know that there isn't. And the idea that gauge invariance generates a massless photon is not true if you include other fields. Now, this is something that today we know, but of course, back then they didn't. It's surprising with hindsight to think that they didn't, but there you are. And as far as I can tell, although this idea is implicit in models of superconductivity that Landau and Ginzburg had written down, the first clear example of a pedagogic nature that I've been able to find was by Phil Anderson in 1963. And I thought I'd just show you this now, because if you take one thing away from this seminar, it could be a genuine pedagogic way of giving the physics background to what we call erroneously the Higgs mechanism, that's completely genuine. It is historically accurate. It is non-relativistic, but apart from that, it has all the features of the real physics. And the key thing about it is that any undergraduate who has met plasmas will understand the physics of it. Or members of the general public who haven't met plasmas, you can at least tell them one fact and the whole thing will go through. So let me just take you through this piece of pedagogy, and it's this. It deals with plasmas. Now, the ionosphere above our head is an example of a plasma. Now, people of a certain age, which means those who probably by now have retired from physics at Nikhef and elsewhere, will recall that back in the 1950s, occasionally, if you were lucky, it was possible to pick up a long wave radio signal from New York, sometimes at night time when the conditions were right. What was happening was that long wavelength radio waves from a radio station in New York heading off into the stratosphere met the plasma layer, the Appleton layer, and were reflected back down to our receivers here in Europe. This is an example of how plasmas do not accept electromagnetic waves below a certain frequency, which is known as the plasma frequency. The reasons why they do not is like first or second year electromagnetic theory. But as a phenomenon, you just accept this fact. The fact that those long wave radio signals bounced off is an example of plasmas rejecting low frequency electromagnetic waves. However, plasmas are quite happy to accept high frequency electromagnetic waves, such as visible light. After all, while that radio signal is unable to penetrate the plasma, we can still see the stars shining through it with our eyes. So there you have a phenomenon. Plasmas do not like low frequency, but are quite happy to accept high frequency. So on this little diagram, the green represents a plasma, and then the red and yellow represent low frequency and high frequency electromagnetic radiation approaching the plasma from the left, the low frequency one failing to enter, and the high frequency one happily propagating right the way through. So now what you do is the Gedanken experiment of imagining that you are a creature that has spent the whole of your life living inside a plasma. This picture shows the spectrum of electromagnetic radiation that you and I are aware of, because we live outside the plasma, but the creature inside the plasma only knows of electromagnetic radiation like that. In other words, the creature will be aware that there is a low frequency cutoff to the electromagnetic spectrum. Now, we imagine this creature is a very bright creature. There's an Einstein creature lives in there. There's a Dirac creature lives in there. And all of quantum mechanics gets derived by these creatures inside the plasma. They know from their quantum theory that the frequency of photons is proportional to their energy. If there is a minimum frequency to the wave, there is a minimum energy to the wave. And if anything that has a lower limit to its energy must have mass. You can reduce your kinetic energy down until you're at rest, but you're left with your mc squared. Only a massless thing can take you all the way down to nothing. So a creature that had their total experience living inside the plasma would perceive electromagnetic radiation to have a minimum frequency, and their quantum theory of the electromagnetic field would be completely one where the photons are massive particles. Now, of course, you and I know that massless photons are polarized transversely to the direction of motion, but have no longitudinal degree of freedom, whereas massive ones also have a longitudinal degree of freedom. It turns out that when an electromagnetic wave hits the plasma, if the wave is of high enough frequency to penetrate the plasma, it also sets up a compression wave inside the plasma, which is indeed nothing more or less than the third degree of polarization. So it turns out that a creature inside the plasma would have a completely gauge invariant description of electromagnetic radiation where the quanta, the photons, act as if massive particles, totally because of the fact that the plasma has been added to the story. If you like, there is another field present. Now, of course, with the creatures inside the plasma, now this is a brilliant idea, but how on earth could you ever know whether it's true? Well, the answer is hit the plasma with just the right frequency, and all the negative charges and the positive charges will coherently oscillate against each other, creating what the condensed matter theorists call a plasmon. So the creature inside this plasma says, let's see if it's possible to hit the plasma with just the right frequency and make the whole plasma excite and prove that it's there. And that is indeed what the plasma Higgs person basically has done. So that's all you need to know for this physics pedagogy, is that we are actually creatures who live inside a plasma. The vacuum is not nothing, it's filled with what we might call Higgs plasma. Precisely what that is, we do not know, other than it's completely blind to photons, that's why they travel through it without gaining any mass at all, but interacts with W's and Z's and ends up with them becoming massive. That is the basic idea. It's the relativistic generalization of that picture that we've just been displaying. And the test of it is if you hit this plasma, this Higgs plasma, with just the right energy of about 125 GeV, you will excite it. And the quantum excitation is what we call the Higgs boson. So that is the picture that Anderson had, non-relativistic. And to show you that I'm just not making this up, this is indeed one of Peter Higgs's two papers in 1964, which eventually led to him sharing his Nobel Prize for his role in this whole saga. And I've highlighted down the bottom, this phenomenon is just the relativistic analog of the plasmon phenomenon to which Anderson has drawn attention. So I think that that is the nearest pedagogy that I am aware of that shows the general concept of us living inside some strange medium, that the interaction of particles with that medium gives them properties which we interpret as mass if we're ignoring the presence of that medium. But at a deeper sense, those properties are all due to their interactions with that medium, and the fact that we have physically excited the medium and demonstrated its reality, which is what the discovery of the Higgs boson is what has turned the whole thing from just theoretical speculation to physical law. It's experiment that decides how good or bad your idea is with regards to whether nature reads it. And so that is one of the arguments that I was making when I researched the infinity puzzle, that although there have been several people, at least 6 back in 1964, along with Higgs, who had had this general idea that the interaction of gauge particles with a suitably designed field would generate masses for those particles. Higgs, Brout, Englert, Gralnick, Hagen, Kibble were the first people doing this. 't Hooft discovered it later independently, as did others. Many people were aware of that. Only Higgs drew attention to the fact that if you excite this medium, you can create a particle that will prove its existence. So although I think it is wrong to call the mechanism after Higgs, because that was many people, I like to call it the mass mechanism. the boson, in my opinion, is correctly named because only he drew attention to the fact that it is the experimentally testable consequence of the whole idea. And it's thanks to that that we now know that the whole idea is indeed valid. Now, I've superposed on Higgs's paper this famous picture of the Mexican hat. If you don't know what all this is about, you're not going to learn it from me now. And if you do know what it's all about, you might wonder why I'm saying anything about it. Well, because along the way, I discovered there's a couple of intriguing little historical things about this that I wasn't aware of beforehand. And having talked with many people, I think many people weren't aware of, not least Jeffrey Goldstone, who was one of the prime movers in this whole business. So what is this little picture illustrating? It's illustrating the potential energy of the vacuum, the idea being that a vacuum that is genuinely devoid of, I'll call it the Higgs field to give it a name, genuinely devoid of the Higgs field has higher energy than one that contains it. So that the presence of this field phi lowers the energy and leads you to a stable state. And this goes along with words like spontaneous symmetry breaking or hidden symmetry. The idea being, if you think of this in a genuine mechanical way, of the red blob there being a real ball sitting atop a real lump like that, at position 1, as you rotate your viewpoint around that, it's completely rotationally symmetric. Whereas at position, when it falls off the top at random, it ends up somewhere in the base, and it can be at anywhere in the base. But having chosen one spot, the symmetry has been spontaneously broken. That's position 2. Now, the history of this was that in the 1960s, starting with Nambu, there was a lot of excitement about whether this phenomenon of hidden symmetry could be key to creating theories in particle physics. It had already been used in condensed matter, in superconductivity by Landau and Ginzburg, but could it be applied in particle physics? And Nambu discovered the idea that if you apply the ideas to chiral symmetry, that the pion, the nearly massless pion, sort of spontaneously emerged from it. The physics being that that ball at position number 2 could be anywhere around the rim, which means that there's an infinity of possible positions. In other words, there's an infinity of possible ground states, and it costs you no energy to rotate from one to the other. So in quantum field theory, if you can have a wave around that base which carries no energy, it corresponds to a particle with no mass. Now, in this model, phi1 and phi2 means there's electric charge present. And so you necessarily are led in this model to the presence of electrically charged massless particles, of which there are none empirically. And these massless particles are known as Goldstone bosons. It was Goldstone who first drew attention to this whole thing. And in the late 50s, around 1960, 61, 2 time, a huge theoretical effort was going on in trying to find ways of evading this, almost like a no-go theorem, which seemed to say you cannot use ideas of spontaneous symmetry breaking because you will always end up with these unwanted massless bosons, which in this illustrative model correspond to the degree of freedom rotating around the base of the rim. Except you can. And what Higgs, by accident, and in my book Elusive will tell the background of this much more, if you add Maxwell's equations to what Goldstone has done, everything changes. In other words, include an electromagnetic field along with this field phi. And when you do that, the equations of motion are written 2a, 2b, 2c on the right there in Higgs's paper. I'll tell you physically what's going on here in a minute, but let's just look at these for a second. Look at equation A and equation C and set E equals 0. In other words, there's no coupling between electromagnetism and the phi field. in that case, you're just recovering what Goldstone did. The first equation is essentially saying that the field, the degree of freedom phi1 is massless. That's the Goldstone boson, the rotating around the base there. Equation C is saying that the electromagnetic field is massless. That is the massless photon. But what we now have by linking the phi field with the electromagnetic field, we have got extra terms in A and C. The equations as they stand there look a bit messy, but what Higgs did was then to rearrange them so that the equations corresponded to the WF nu being massive, and the Goldstone boson, which previously was there, has become transformed into the longitudinal degree of freedom that the massive photon or gauge boson has to have compared to the massless case. So that is basically the relativistic basis to the Higgs observation, that you can create massive gauge bosons by gobbling up the Higgs boson. But what about equation B, which involves only the field, only the degree of freedom phi2? Phi2 corresponds physically to the ball rolling off the top and oscillating up and down either side of the rim, the base of the valley, up and down the walls at the bottom. And in quantum field theory, that corresponds to a massive mode. Equation 2b is the equation of motion of a massive boson, and that is indeed what we call the Higgs boson. Now, the reason why I'm showing you all this, and I apologize to those of you who know this much better than I do, is to go back 3 years to Goldstone's 1961 paper, in which he used this model of the Mexican hat and showed how it led to these unwanted massless Goldstone bosons, which are the degrees of freedom as it rotates around the base of the rim. But in his paper, he has an equation of motion for the infinitesimal oscillations up and down the minima. And that is the equation of motion of the massive boson. So what we call Higgs's boson is actually Goldstone's other boson. It's already in Goldstone's 1961 paper. But he wasn't interested in that. He was interested in the phenomenon of the massless bosons that necessarily arise with spontaneous symmetry breaking. And of all the people that looked at this, only Higgs drew attention to the physical role of the massive boson. Jeffrey Goldstone told me that he had also included electromagnetic field in his original work, and he spoke to Schwinger about it in 1961 during a sort of coffee break at Harvard, where Goldstone was at the time. And Schwinger's reaction was something along the lines of course you get massive photons, as if it was well known. So it would seem to me that Goldstone was doing this around the same time that Schwinger was going through his transition of realizing that massless photons and gauge invariance are only true in perturbation theory and not necessarily generally true. When Goldstone made this remark to him, Schwinger already in some sense knew it. And unfortunately, Goldstone never made the comment himself. Otherwise, history would have been very different. But there we are. So Higgs alone of these people mentioned the massive boson. The ideas at the time made almost zero impact. In fact, Peter Higgs showed me this nice letter he got from Walter Gilbert in August 64 saying, "Thank you for sending me preprints of your two papers. Unfortunately, I believe your conclusions are wrong." The real paper that did it for Higgs was 1966, when he developed the ideas. And in particular, I'm just going to make one further comment. Here we've got the manuscript of a paper that never appeared, which is the follow-up to his 1966 paper, same title, but number 2, non-trivial symmetries. Higgs had the idea. He was now trying to find an application of it and was trying to apply it to the strong interactions where the rho plus, the rho minus, the rho and omega and so forth could be the massive particles. And so he was trying to generalize it to non-trivial symmetries, but he was never able to make it work. And so he never published this paper. But there's a manuscript of a paper that he didn't do. He hit a barrier, just like Weinberg hit a barrier trying to apply it to strong interactions. But of course, Weinberg then had the insight that if he applied it to weak and electromagnetic interactions, things might work. But I'll come to that in a second. So the key thing in Higgs' 66 paper is that he included a section where the massive scalar boson, the Higgs boson, decays into two vector bosons. These are bosons that have gained their masses through the mechanism. And in equation 17 that I've highlighted, the amplitude has the mass of that vector boson explicitly in it. And Higgs in his paper also discusses the possibility of fermions gaining their masses by this mechanism and showing a similar phenomenon, that the scalar boson decay has amplitudes proportional to the mass of the particles. And that is the key feature that distinguishes the Higgs boson from other particles, that the Higgs boson has an amplitude for decaying to particles in proportion to the masses of those particles. And that today is the key thing that has been used to establish that the boson that has been found is indeed the real deal. But why is it named after Higgs? And I thought I'll just quickly go through a little bit of history here before coming to the end. Weinberg made this famous theory of leptons in 1967, where he took what we now call the SU2 cross U1 model, which he had independently now stumbled upon, and added spontaneous symmetry breaking to it, or the Higgs mechanism to it, to make a potential theory. And the first this appears in the world, as far as I can find out, is at a Solvay conference in 1967 that H.P. Durr had been giving a talk about the Goldstone problem. And then at the end of his talk, Weinberg made a comment where he describes to the audience the fact that he's using spontaneous symmetry breaking, adding it to the SU2 cross U1 model, and then says, this raises a question I can't answer. Are such models renormalizable? Now, Engler of Engler and Brout was present, and he makes some remarks that Brout and he have been looking at this, blah, blah, blah. And he concludes that the answer to Weinberg's question is that these massive vector gauge fields constitute a renormalizable field theory. Now, I don't know what Engler and Brout had done, but they clearly had not solved the problem of renormalizability, given the amount of effort that Veltman and 't Hooft had to take in order to do that very thing. But at least at that stage, intuitively, Weinberg was believing that this would be a renormalizable theory, though he was never able to prove it himself. And after Howard and Veltman had completed their work, and Weinberg had published this paper, the model of leptons, which only received a handful of citations for 4 years until the appearance of 't Hooft and Veltman's work, at which point it became the most highly cited paper in particle theory. And I think it's now had 10,000 citations or more in total. From T.D. Veltman, I got this copy of Weinberg had sent his paper to 't Hooft. Dear Dr. 't Hooft, this letter suggests, though it does not prove, the renormalizability of the massive Yang-Mills models discussed in your recent preprint, in which the vector meson mass arises from spontaneous symmetry breaking, SW. So he sent that to 't Hooft in 71 after their work first appeared. Now, what you see also on here is the handwritten manuscript of Weinberg. And this is where something very interesting comes out. Because on the left, I'll just show you the front page. On the right are the references, and they're not very clear on your screen. I'm not sure if right. I'll just say, have a look at reference 3, where he cites Higgs, physics letters, phys rev, blah, 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 blah. This is what appears in his paper. The published paper, as I said, the most highly cited papers in theory since, has got the reference to Higgs, 3 papers, then Engler and Brout, then Guralnick, Hagen, and Kibble. The point of this is that Higgs's name has been cited first. Now, historically, Engler and Brout's paper appeared first. But Weinberg has put Higgs's name in pole position. And this is what started the impression that it was Higgs that was in pole position. And you can now see how this came about, because I've enlarged it slightly. I've compared his printed version here with his handwritten version, and you can see what has happened. He already knew of Higgs's work because he had met Higgs earlier that summer at Brookhaven where they had both talked about their attempts to try and apply these ideas to the strong interaction and had both failed. Higgs gave up. He never published that paper whose manuscript I showed you. Weinberg went away, had the insight that he was applying the right idea to the wrong problem and applied it now to weak and electromagnetic. That's how he knew of Higgs. He's taken his manuscript with him to this conference, and at the conference has learned from Brout and Engler of their work, and also has learned from Tom Kibble at Imperial College of Guralnick, Hagen and Kibble. And so you see in little writing here, he has added a memo, Hagen et al., Brout and Engler. And when he's got back to Harvard, has completed the work and put them in, but he's put them in afterwards because he knew of them later, even though Engler and Brout had done it earlier. So that is how Higgs's name coming in pole position started off. Well, finally, of course, after much effort, Toft and Veltman proved that indeed the idea of Yang-Mills theories is renormalizable. And if you use the Higgs mechanism, as we will call it, you can get a gauge invariant renormalizable theory with massive gauge bosons. So there they are, the two of them showing Teeny with the idea of somebody climbing a mountain and finally getting there. So I just thought I would end by just recalling then what happened. So the Nobel Prizes, and strange bit of history. Glashow has made his SU2 cross U1 model in 1961. Salam and Ward come up with it 3 years later. Weinberg has come along with the same SU2 cross U1 idea and added the idea of applying spontaneous symmetry breaking to it in 1967. Salam picks up on this idea 1 year later. In 1971, Toft and Veltman show that indeed an SU2 cross U1 model with spontaneous symmetry breaking is indeed a renormalizable viable theory, what we now call quantum flavor dynamics. And this becomes strangely known as the Weinberg-Salam model. Now, why it should have been is a story in its own right, which you can read about in the book. It raises the question of what happened to Ward. Well, there's Ward and Salam, a picture that Dave Jackson once took. And in the brochure I found years ago at Trieste, you see Ward completely airbrushed out of the story. Anyway, however it came about, Ward was not included in the Nobel Prize for Glashow, Salam and Weinberg. He was the missing fourth man. And in that sense, he shares a place in history alongside Freeman Dyson, who was the missing fourth man at the start of this whole story. So that is the punchline. 50 years ago, it was finally demonstrated that you can make a viable renormalizable theory of the weak and electromagnetic interactions, and by implication also QCD, but of the weak electromagnetic interactions with massive gauge bosons, so long as the mass is generated by the mechanism that Higgs and Engler shared a Nobel Prize for later. Engler's collaborator Brout, sadly, having died in the interim, never living to see the whole glorious thing verified. Because indeed, in 2012, the boson itself was discovered, and this beautiful piece of artwork, which is in fact a genuine physical event of a Higgs boson decaying into 4 muons, was demonstrated to be true. So if you like, the plasmon had been found. So that's all I have to say now, other than to give my plug again, that I'm currently in the process of going over, hopefully one last time with Peter Higgs, my attempts to tell not so much his biography as the biography of what happened. And I leave you with that photograph of Higgs and a Toft at Eritrea in the strange days when we didn't know for sure that nature really worked this way, but nature already did and was about to tell us. So thank you very much, and I hope we can now get back to talk to each other.
Well, thank you, Frank. Very nice talk. Some steep slopes for me as a relative amateur, but still, it's intriguing to see how all this stuff actually comes about. I'm sure there's some questions or remarks from the audience. So if anyone has a question, please unmute yourself and go ahead. Chris Gotthard-Altes.
Yeah. Okay, Frank, very nice talk. Do you hear me?
Yes.
Okay. So Ward, of course, is, well, it's a sad story in a way. But of course, he never wrote a paper saying that the Higgs mechanism played a role, right? In his 64 paper with Salam, there is no talk about Higgs.
Correct.
So in that sense, well, okay, he saw the symmetries, okay? But he didn't see the Higgs mechanism. Incidentally, like Shelley Glashow, who even, I talked to Shelley in 71 at the Bologna conference. It was in March 71, and Shelley was not believing at all in the Higgs mechanism, and he said this whole paper of Weinberg is completely wrong. And he even talked about a certain Mr. William Crapper who invented the water closet, things like that. So anyway, the for Ward, of course, it was the main issue was that he had nothing to do with the Higgs mechanism, right?
That's correct. I mean, that Ward played no role in the Higgs mechanism. It is a moot point as to what extent Salam did, but that's another matter. One thing I do mention in Infinity Puzzle, which is a real irony, seeing as you've mentioned Ward, deals with Guralnik, who was part of the, thank you very much, was part of the Guralnik, Hagen and Kibble trio at Imperial College. A lot was happening in 1964. It was 1964 when Guralnik, Hagen and Kibble discover what we call the Higgs mechanism at Imperial, and it was 1964 when Ward and Salam finally stumbled on SU2 cross U1, also at Imperial. And apparently Guralnik and Ward went to lunch together one day, and Guralnik, who was a young postdoc and very nervous, starts talking to Ward about what he's doing, and Ward, who was very paranoid, said, "Have you published any of this you're telling me?" And Guralnik said, "Not yet." He said, "Never talk about your unpublished work. People will steal it and take it away from you." So they talked about something else. And I thought, well, just imagine if that conversation had continued. Guralnik would have been telling Ward that he had a mechanism for giving mass to gauge bosons. And Ward would have told Guralnik, "Oh, SU2 cross U1 with massive W's and Z's, you found a mechanism for giving masses to those. Let's write it up together."
But that's of course what if history, right?
Yes. But it's another message, never be afraid to talk.
Yeah, well, that's a good point, I guess. Keep talking.
Or at least to people you trust.
Being paranoid doesn't help to get your ideas known.
Any more questions or remarks? Yes, Tom, go.
Yeah, Frank, thank you very much. Very nice presentation.
Hi.
I didn't know the story, what you were mentioning about the pole position of the paper of Higgs in, or the reference to Higgs in the paper of Weinberg. And I was wondering, do you know who first coined the name of Higgs particle? Because I thought that was then actually done later by John Ellis.
You're asking a very good question. One of the things that I have been trying to establish in Elusive is that very thing. And John Ellis certainly played a role in the sense that, well, first of all, Weinberg, having put the references in that order, further compounded the problem in 1971 when he wrote, following the 't Hooft and Veltman, Weinberg then wrote a further paper on all of this, in which he gave the wrong reference to Higgs. Higgs had published in Physics Letters, volume 12, but Weinberg referred to him as Phys Rev Letters, volume 12, which made it look in front of Brout and Onglair, who were Phys Rev Letters, volume 13. So that further compounded the error. 1976, Ellis, Gaillard, and Nanopoulos wrote the first phenomenological paper on how one might go looking for what we now call the Higgs boson. And And they referred to it as the Higgs boson, I think even in the title of the paper. So now all the experimentalists sort of knew of it as the Higgs boson. I don't think there was a moment in history when it suddenly became the Higgs boson. Peter Higgs always refers to it as the boson that's been named after me. There certainly was a time before it was known like that, and there was a time after which it was always referred to that. But I haven't found a sort of theta function change.
Yeah, okay.
Okay. Anyone else?
If anybody has any insight into that, please let me know.
Yeah. More questions, Karel? Karel Gamers?
Okay. Frank, first of all, a very good talk. I enjoyed it enormously. I'd like to come back to the question that Stan asked. When was the Higgs boson the Higgs boson? And indeed, I always thought that paper by John Ellis, Miri Gaillard, and Anopoulos, which in the title has the phenomenological profile of the Higgs boson. So
Correct,
that was,
yes.
the Higgs boson was in the title. Not only that, I believe that was the paper which contained a long program to search for a Higgs boson at 1 keV, at 1 MeV, at 1 GeV, etc., etc. So they really presented the whole menu of where to look for the Higgs boson. And first of all, I thought this was very influential for the experimental community. And I think the name Higgs boson caught on there. So that's one thing. I think the other thing, at some point in Great Britain, Margaret Thatcher wanted to know why CERN wanted to look for the Higgs boson, and there was some kind of contest for the best explanation. And I think that's the other point where the Higgs boson became a household name. But on that second point, I'm less sure.
I agree with you totally on the first one, and partly on the second, actually. One of the things that I say in Elusive, I can't pull up the actual quote at the same time as operating this, unfortunately, but I say that you're right. In the title of the Ellis, Gaillard, Nanopoulos paper, I said that now the Higgs boson had suddenly been advertised to the experimental community, even if they read no further than the title, is what I said. So that is certainly true. Yeah. The other thing, I mean, with regards to the Margaret Thatcher, it was more the science minister, William Waldegrave, who we're now talking 1980s. This is around the time when the SSC had been first proposed and then terminated. And there was serious worry that the whole program of particle physics in this direction was going to fold. And Waldegrave issued this challenge to the particle physics community, saying, look, you're asking for all this money to build this machine at CERN. If you can explain to me in a simple way that I can then present this, if you like, in Parliament. And that's how this famous competition came up. One of the entries being the idea of Margaret Thatcher entering this room and so on and so forth. But that was quite late on. But one of the things that I say in Elusive along these lines is that in a way I feel quite sorry for Peter Higgs, strangely. I mean, he's a very shy, withdrawn person. I don't know how many of you, if any, have ever been to a conference. And if you have seen him there, have you ever heard him speak or ask a question? I just raised that. It's almost a rhetorical question. And in a way, he was used. And I said that it's easier to follow. I mean, he was used as a totem, in effect, for this whole process. And as it is easier to follow a slogan than an abstract idea, that is how Higgs' name was used by the particle physics community in order to promote the whole enterprise. The God particle certainly helped it as well. But one of the consequences of this, which Peter Higgs said to me almost after the discovery, he said, what he worries about is that his name had been used so much to promote the LHC. Now they found the boson, people are going to say, well, turn it off, you don't need it anymore.
Yes.
That's an actual problem people are talking about right now. But still, we have to move forward. I see a question from Beatrice. You have no sound on. Beatrice, are you there?
It was
Yeah,
David
okay,
Miller,
okay.
by the way.
Yes, it's about precisely in which moment someone called the Higgs boson or Higgs particle. This guy, I remember, I read like 3-4 years ago or less, a text of Higgs, Peter Higgs. I don't remember it was an article or an interview. This I don't remember, but it was something recent, very recent. And he was explaining precisely this. He was explaining exactly in which moment someone has the idea to call it Higgs particle. And perhaps it was during a conference, but I don't remember exactly. But he was explaining this. So Peter Higgs knows perfectly.
Right. Okay. I now know what you're referring to. Yes. It was in Peter Higgs in 1967 was in America. That's when he spoke with Weinberg, and they both realized they were applying the right idea to the wrong problem. Peter Higgs then was at a conference where Ben Lee was talking to him at a cocktail session. And Higgs was explaining to Lee the physics of all this idea. That is how Ben Lee became so much involved in this. And then you're completely right. It was 1972, the conference in Chicago. This is after Toft and Veltman have now produced their explanation of quantum flavor dynamics. And there's a whole session devoted to this that Ben Lee was the rapporteur for. And it was inspired by Toft and Veltman's work. And all of the talks, however, are plastering Higgs's name. All those talks keep referring to the Higgs mechanism and the Higgs boson and so forth. And so I think and Peter Higgs said that it was Ben Lee plastering my name over everything that did it. Well, actually, to be fair to Ben Lee, it wasn't Ben Lee plastering his name over everything. It was all the speakers in that session. But thank you very much, Beatrice. That was it. It was the 1972 conference where it all began, I think.
Okay. I've taken a look at the clock. It's over one o'clock even. So we have to end this session. People are leaving for other sessions as well. I'd like to thank Frank Close again for your excellent talk. I'd like to recommend your previous books and your future books. Thank you so much. And I took a note from what you told us, or what you showed us, which was a paper from Salam and Ward in 1964. And the first sentence mentions dreams in elementary particle physics. I can hardly imagine any papers appearing now with those words up front, but it would be nice, wouldn't it?
Indeed.
Okay.
Well, thank you very much. Thank you very
yes.
much for hosting this whole thing. And I hope after Elusive appears that we'll be able to meet in the real world and come across and enjoy Amsterdam together.
Yes, you're more than welcome anytime. So for all others, thank you for being here. See you next week for the last lunch talk. We have a new neighbor talking about Amolf. So be welcome to join us then. Thank you for now. And as always, stay safe. Bye-bye.
Bye-bye. Good old
Thank
friends.
you. Bye-bye.
Bye, Frank.
Bye.